Dear students, this video is on calculation of within and between sum of squares and test statistic. Now we proceed to calculate the test statistic value. To calculate the test statistic value, we require what is sum of squares for treatment and sum of squares for error. So now let us find out sum of squares for error, that is within sum of squares. So here within sum of squares is computed in 3 bunches. So first we are going to find out the deviation of observation from the first group mean, and then we are going to take the squares and then add it up. Similarly, in the second bunch we are going to take the squares of deviation of observation in the second group from the second group mean. Similarly, in the third set we are going to find out the squares of deviation of the scores from the third group mean. So after adding all these observations, we will end up with the within sum of squares, that is 989.6. Now we will calculate the between sum of squares. For finding out between sum of squares, this is the formula: summing over I ranges from 1 to k the size of the group multiplied by the squares of deviation. We compute this sum by 3 different bunches. Let's say for the first bunch we are going to take the squares of deviation of the first group mean from the overall mean and multiply with the size of the first group, and then in the second bunch we are going to find out the squares of deviation of the second group mean from the overall mean and multiplied by the size of the second group. Similarly, in the third bunch we are going to find out the square of deviation of the third group mean from the overall mean multiplied by the size of the third group. So after substituting these values, we have already found out y1 bar is 25.6, y2 bar is 44.4 and y3 bar is 9.6. After finding out all the squares of deviations and then multiplying with the corresponding size, we will get 3034.1. So the sum of squares for treatment is 3034.1. Now we will calculate the degrees of freedom for between sum of squares. As we discussed earlier, the formula is k minus 1. K is the number of treatment we are comparing, so it is 3. 3 minus 1 is 2. So there is 2 degrees of freedom attached to the treatment. And then the degrees of freedom for the total sum of squares is n minus 1, that is the total number of observation, pooling the scores of all the group, that is n1 plus n2 plus n3 minus 1, we will get 14. The degrees of freedom for within sum of squares is, we have to subtract the between degrees of freedom from the total degrees of freedom, that is 14 minus 2, we will get 12. So the degrees of freedom attached to treatment is 2, the degrees of freedom corresponding to the total sum of squares is 14, and the degrees of freedom attached to error is 12. After finding the degrees of freedom, we will calculate the variance of within sum of squares and between sum of squares. So we have already introduced the formula for within group sum of squares, that we call it as within group variance. So since we are estimating from the sample, we call it as estimate of within group variance, that is denoted by SW square. Some statistical textbooks you can see MSSE means mean sum of squares due to error. So that is why E is given in the subscript. So the formula for mean sum of squares for error is sum of squares for error divided by degrees of freedom for error, which is equal to 82.5. And then we will calculate what is the estimate of between group variance, that is mean sum of squares for treatment. It is represented by SB square. It is the ratio of between sum of squares divided by the degrees of freedom for between sum of squares. So the value is 15.17.1. So after finding out the estimate of within group variance and between group variance, before actually calculating the test statistic, we will try to interpret, or we will try to come to an approximate idea of whether to reject the null hypothesis or alternative hypothesis, we will look at the value of mean sum of square for treatment and mean sum of squares for error. So, when you look at the mean sum of squares for treatment, it is 3034.1, which is more than the mean sum of squares for error, which is 989.6. So, we get an idea that this difference is more likely to reject our null hypothesis, but we do not know how large must be the mean sum of squares for treatment to reject H naught. So, different people will come to different conclusion. So, for a uniform criteria, we have an objective calculation called F statistics. So, we calculate the F ratio by using the formula mean sum of squares for treatment divided by mean sum of squares for error, which is 3034.1 divided by 989.6, which gives you the 18.4. After calculating the test statistic value, we will find out the critical value from the F table, so that we can make a decision whether to reject or accept the null hypothesis. So, the figure which is given here is a distribution curve of F distribution, and we can obtain the critical value for 2 degrees of freedom in the numerator and 12 degrees of freedom in the denominator from the table, which is already displayed to you, which is 3.89. So, what this represent in the figure is, so 3.89 is exactly the line which is intersecting vertically on the curve. So, at this line we have the F value as 3.89. So, when your calculated test statistic value is going to fall after this line, okay, we are going to reject our null hypothesis. So, in testing of hypothesis, we have rejection region and acceptance region, which is been discussed with you in the previous module. So, once your calculated value is falling after this line, then you are going to reject your null hypothesis. So, now we will check whether our test statistic value is falling above this line or not. So, we have calculated our statistic value is 18.4. So, definitely it is going to fall after this line, that is in the colored region. So, we are going to reject the null hypothesis. Otherwise also we can calculate. So, the critical value is coming from this F table. So, this table is giving you the critical value for F test. So, the columns represents the numerator degrees of freedom, the rows represents the degrees of freedom for error. So, we are having 3 treatment. So, the degrees of freedom associated with the treatment is 2. So, we are looking at the second column, and the error degrees of freedom is 12. So, intersection of this 2 and 12 leads to 3.89. So, that is why we are getting the critical value as 3.89. Now, we shall discuss the alternative method for computing the F statistic. In the previous calculation, we have obtained the sum of squares for treatment and sum of squares for error, and then we have obtained the mean sum of square for treatment and mean sum of squares for error, and then we have calculated the ratio. But there is an alternative method. We no need to calculate the within sum of squares. We can subtract the sum of squares for error from the total sum of squares. So, we will see how to find. So, once you have computed the between sum of squares and total sum of squares, we can subtract between sum of squares from total sum of squares to get the error sum of squares using this formula. So, how to calculate the total sum of squares? So, previously we have explained only the error sum of squares and the between sum of squares. We never discussed how to calculate the total sum of squares. So, how to find the total sum of squares? It is by summing all the squares of deviation of all the scores from the overall mean. So, that is, we are subtracting 22 from the overall mean 26.5 and 23 from 26.5. So, like that we will do for all the observations, and we will end up with the total sum of squares, what is called 4020.7. So, with this we can able to find out within sum of squares, and other calculations are similar. We can use the ANOVA table to find out the test statistic. Till now we have calculated the total sum of squares, error sum of squares and between sum of squares. Based on all these three values, we have explained how to estimate the F statistics value and how to get the table value from the F table. We will meet in the next video. Thank you.